Okay, hi everyone, and welcome back to another video. So in this one, we're going to be looking at binary search. So this is a much more efficient and better searching algorithm than linear search. However, it does have the precondition that the data that we are searching through must be ordered. As a really key point, we cannot ever do a binary search on unordered data. It must be sorted either in ascending or descending order. Okay, so let's take a look at how this works. So you can see we have a big array of data here, and that we're going to do a search for the target 88. Okay, we've also got 3 pointers here. We've got min, mid, and max. Okay, so basically what these do is min indicates the smallest, the lowest possible index where our target could realistically exist. And max does the largest, the highest possible index where our target might exist. And as you can probably expect, mid is kind of the midpoint between min and max. Okay. The utility of these pointers should become clear once we start searching. So let's just dive in. So basically, the way that binary search will work is that we find the midpoint between min and max, and we just ask ourselves, is this our value that we're searching for? Okay, so we're going to start off by searching this this position here in position 7, this 25. Okay, now we can see clearly that 25 is not equal to 88, but we have to ask ourselves, is it larger or smaller than our target? So our target 88 is clearly much larger than 25. So because this is sorted, it is not possible for 88 to exist anywhere in this half of the array. Okay, there's no point searching the places where we know all of the values are going to be 25 or less. Okay, so we're not even going to look at these. Okay, so these kind of get like removed from the search domain. Okay, now the way that we remove these from the domain is that we adjust the pointers. So the lowest, after we know that 25 cannot contain our target, the lowest possible index that could contain our target is going to be the one after mid plus 1. So min basically jumps up. Okay, then we have to recalculate our midpoint by finding the midpoint between our new min and our max, which did not change. Okay, so we can see here that we have 7 elements remaining. Okay, so let's put our mid right here in the middle of min and max. And then we simply repeat the process. So we're going to search 82 this time, and we're going to ask ourselves, how does this compare with our target? So 82 is still smaller than our target. So that means that we can basically just do the same process again, where we know that there's no point searching anything lower than what we just searched. Okay, so we can also disregard these elements. Okay, we only have 3 left now, and our min pointer moves up again. Okay, just like that. It's a little hard to read. Let me extend this arrow just to make my examples a little bit clearer. Okay, so you can see that our midpoint is going to be between our min and max. So this time we're going to search this value. Okay, now 90 is still not equal to our target. However, this time 90 was actually bigger than what we're searching for, which means that we disregard anything bigger than this index. So we only have one thing that's bigger than this index in this case, so we're going to disregard this one. Okay, and at this point, min and max are going to have the same value, and therefore mid will also have this value, and you can see that we have finally found the value that we are looking for. Okay, so that's how binary search works. It's the continual testing of the middle remaining element, and then removing half of the possibilities each time depending on the outcome. Okay, so let's examine how to code a binary search algorithm. All right, so you can see here I've got some data here that I'm going to be searching. Remember, the data must be ordered. This will not work on unordered data. All right, so let's declare our procedure. And we're going to take one parameter, and that parameter is going to be our search target. Okay, so for example, if I want to search for 14, I'm going to put 14 in these brackets when I call it. Okay, so because we're dealing with integers, let's make this parameter an integer. Okay, so let's do a little bit of setup. So we need to set up our min and our max. So our min is always going to be 0, assuming that our lower bound is 0. In exams with pseudocode, sometimes you'll get the situation where you're dealing with an array where the lower bound is 1. So in that case, your min would be 1. But in real programming, and certainly in Python, array lower boundaries are 0. Okay, so we're going to set our min to 0. Whatever the index of the first thing is going to be, that's your min. Okay, your max is going to be the length of your array minus 1. Again, assuming that you start counting at 0. If your lower bound is 1, then you're going to have your min and max like that. But when you're coding, pretty much all cases, you're going to have it like this. So that's your min and your max. Now, we're not actually going to set up our mid yet. We're going to do our mid inside our loop. A couple other things we need to do is basically we're going to have a while loop. Okay, and we're going to have two parts to our condition, and one will be while found is false. Okay, so we're going to keep doing our loop, keep doing our little divide and conquer until we find what we're looking for. And of course, we need somewhere to store store the position of what we found. So just like with linear search, we're going to use -1 as a kind of failure indicator. All right, so if this outputs -1, it means we haven't found what we're looking for. So we're going to start off at -1 and see if we can change that to the index of our target. Okay, so this is the setup that we have. So our condition, so we do, well, found equals false, and so found equals false. This will allow us to exit early if we find, if we find our target before we exhaust all of the elements. But to handle the situation where we never actually find it, so if you remember in our last example, which we can go back to actually, these min and max pointers kind of moved in on each other as we went through, and eventually they were equal. If we didn't find our target, what would have happened? Let's say that this was actually 89, okay, and we were looking for 88. What would have happened there is max would actually have gone over here, because 89 is too big, so we've got to reduce our max by 1, right? And then we'd have the situation where our max is actually smaller than our min. And that's the indicator that we haven't found what we're looking for. It doesn't exist in the array. Okay, so max being at least equal to min is a condition for continuing to search. Okay, so in our loop, the first thing we do is we calculate our midpoint. Okay, so if you remember, then the midpoint should be exactly halfway between min and max. Okay, so here we have 1, 2, 3, 4, 5, 6, 7 elements in our range. So you would basically expect the middle one right here to be equal to our mid. Okay, so the way that we can do that is by doing min plus max div 2. Okay, now this is very important that you don't just do regular divide, which is this symbol. You do div, which is this symbol. In pseudocode is written as div, like that. Okay, and remember that this is integer division, div. Okay, so for example, if I did something like 13 div 2, the answer is 6, right? 13 divided by 2 is 6.5. Okay, but in integer division, we only keep the integer component of the answer. Okay, so that's what we're doing here. The reason we need to do that is because if we end up, we're going to use mid as an index, and that can only be an integer, right? Remember, an index would be to point to one of these positions. So if I got something like 6.5, that's going to throw me an error because there is no index 6.5, there's only 6 and 7. Okay, all right then, so that's our midpoint. Okay, so basically we just have an if statement inside our loop. So we're going to check to see if the data at position mid is greater than our target. Okay, data at position mid is greater than our target. Okay, if that is true, okay, so what happens when that's true? That means that so let's say for example, if this is our mid right here, but we were searching for 18, let's say, right? What that means is that the max cannot be anything higher than this one. Okay, the midpoint is too big, which means that we can only look at smaller things, which means that the max can only be at most the one before midpoint. Okay, so we're going to set max to mid -1. Okay, now let's deal with the opposite condition. Let's do if data mid is less than our target. Okay, we do kind of the opposite thing here. We'll do min equals mid plus 1. Okay, so let's look at the example. Okay, so let's consider that we are looking for 51 this time. okay, in this example here, right? So 25 is too small, which means the mid should go right here, because the smallest possible element that could contain what we're looking for is the one after mid. So we do min equals mid plus 1. Okay, so basically if neither of these things are true, if the data at mid is not bigger and it's not smaller than a target, then that means it is equal, which means we have found what we're looking for. Okay, so what do we do then? First thing is we store our mid. Technically you don't need to do this, you could just output mid, but I think it's cleaner to use its own variable, especially with the whole -1 condition. It makes it a bit cleaner if you use a separate variable for position. And we also have to set this found condition to true so that our loop will not keep running. Okay, so this will work. All that is left is to output our results. So I'm just going to put a print statement right here, print our position. Okay, and that is our completed algorithm. Let's run it a few times and make sure we've coded it correctly. Okay, so let's look at data first. You can see that it's there, it's sorted, and let's do binary search for 14. And you see it's output 6. Now, is that correct? Remember, this is the index of what we're searching for. So 0, 1, 2, 3, 4, 5, 6. You can see 14 is at position 6, so that looks good. Okay, let's try a couple more for things that we can see. So let's try 7. So what? Before we run it, let's predict the output. So 0, 1, 2, 3. Okay, so this should output 3, and you can see it does so. And let's do one more. Let's try for 22. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I would expect binary search 22 to output 9. And it does. Okay, let's try binary search. Let's do 17. Now 17 is not in this array, so what output are we expecting? So if you remember the way we coded this, I would expect an output of -1. Let's try it. Fantastic. And let's just do one more for good measure. Binary search of what happens when we search for -1? We get -1. Okay, meaning that it's not in our array. Okay, so that is your binary search algorithm. Okay, so again, just like any of these algorithms, you should be comfortable with a few variations. So some variations you might see is you might see this implemented as a function where the position gets returned. And if you do that, what you can actually do is you can just return at this point and then return -1 at the end. I'll quickly model that actually. Okay, so here what we can just do is return position, which means we don't actually need this found equals false. And then if we never hit this, we can then return -1 at the end. Okay, so we actually don't need, we can actually just return mid, even shorter. Okay, remove this position, remove this false. Okay, so let's run this one. Okay, so if I do something like x equals binary search 14, and look at x, you see I still get the same result. If I do x equals binary search and we'll do 0 for something that's not there, and print x, you can see -1. Okay, so that still works, and this is implemented as a function with return statements. That's another common way of doing it. This is actually a really good way of doing it if you're coding it for yourself. Okay, so another way that you can write binary search is you can actually write it as a recursive function. So if you haven't learned about recursion yet, I don't recommend that you watch this part of the video. It'll probably be a little bit too complicated. But if you have learned about recursion, then I strongly recommend you get a very good understanding of binary search, because binary search is actually one of the few algorithms that are relevant to you where recursion is useful. Okay, and don't worry if you find the code a little bit hard to follow. We are gonna, you're gonna have an opportunity to do a full trace, and if you're not sure how to trace it, I'm also gonna trace it for you. Okay, so you'll be able to see exactly how this works. Okay, so let's take a look. So we're going to define our recursive binary search function. So we're going to have a few more parameters. We're going to have min, max, and target. Okay. The idea being that every time we recurse, we're going to have either a different min or a different max compared to the last time. So we're going to have to define the min and the max when we call it. Okay, so we do our test inside if max is greater than or equal to min. Let's first of all, let's calculate our mid, obviously. So that remains the same as the iterative version, min plus max div2. Okay, and now we've got our selection statement. So if data mid is equal to our target, that means we can simply return mid, because that's our position, right? Which will end the recursion. It'll start to unwind, and it will give us back our final answer. Okay, if it's not equal, then we're going to recurse more. So basically, we're going to have to decide, are we recursing to the small side of the search domain or the large side of the search domain? So if data mid, let's start off with data mid being too big. So that means that we are going to return a recursive call to the same min, but the max is going to be mid minus 1. Okay. Now, obviously, if I wanted to make this slightly clearer, I could do here like max equals mid minus 1, and then just do min max. You might find that easier to follow. But, you know, it's an unnecessary step, so I'm just going to do mid minus 1. Okay? And then the target remains the same. Target never changes. Okay, then. So let's pause and look through our data, just if you're a little bit unsure what's going on here. So let's imagine, so our midpoint is going to be 10, I think. Yes. Let's imagine we're looking for 6, and we've done 10 on our first call, which means that data mid is bigger than our target. So that's this condition. So what we're going to do is our min is going to remain the same at 0, but our max is going to be mid minus 1, which is this one. So that's where min and mid minus 1 come from. Okay, so let's deal with the opposite case where data mid is smaller than our target. So in this case, we're going to return binary search, but we are instead of the min, we're going to do mid plus 1. Keep our same max and keep our same target. Okay, so let's think about this one. Imagine that we are searching for 18 and 10 is our mid. So the minimum is going to be this one. Okay, which is mid plus 1. So that's where that comes from. Okay. All right. So that's basically our recursion element dealt with. So this will continue to recur as long as this is true. We just need a little else to handle if this is not true. And this means that we haven't found our target. So we're going to return minus 1. Okay. So that's actually all we need. So we can actually call this if I run. Okay, so we can do binary search. So our min is 0. Our max is going to be length of data minus 1, right? And our target is 14. Okay, so if I run that, you can see I get the position of 14, which is 0, 1, 2, 3, 4, 5, 6. So that is correct. Okay, just to make testing this easier, I'm going to set up a helper function where I only have to pass in a target, and it works everything out for me. Okay, so I'm just going to call binary search with 0, length data, basically the same parameters I used over here, apart from the target, which is going to be equal to whatever I pass as a parameter to this helper. Okay, so now I can just call search with my target, and it's a little bit easier to test. Okay, so let's search for 14. Cool, so you can see I'm still getting 6 back. Search for 100 should be minus 1. Search for 7, that should be 3. Search for 22, that should be, let's see, is that right? 6, 7, 8, 9. Yes, that's correct. Okay, so looks good. This is a recursive version of binary search. So again, don't worry too much if this was confusing. I'm about to do a full trace of this algorithm. Okay, so we are going to do a search on this data up here for the value 14. Okay. So we're going to start off by calling our binary search function. We're going to give it the min, which is 0. Max is going to be, well, it would be length of data, but let's work it out and give it a real number. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that's our max. And our target is 14. Okay, so now we're going to draw this arrow symbol, which indicates that the function is being called. Okay, so this is the first call. And now the clearest way to do this is just to kind of list out the variables that exist. So let's start by specifically saying what our parameters 0, 9, and 14 are. So if we just look simply at the order that they're specified, we can say that our min is 0, our max is 9, and our target is 14, right? All that information is just coming straight from the arguments, and I'm just kind of lining them up with the parameters just to give them names and make it a little bit clearer what is what. Okay, so you can see that max is indeed greater than or equal to min. So we're going to go and work out our mid. Okay, so what is our mid? So our mid is min plus max div 2. So 0 plus 9 div 2 is going to be 4. Okay. Now, just for a little bit of extra clarity, this if statement that's coming up relies on data mid. So let's just work out what data mid is before we go. So mid is 4, so data 4 is 0, 1, 2, 3, 4. Okay, it's 10. Okay, so we can keep that in our mind to make this comparison a little bit easier. So basically we're asking ourselves, is 10 equal to 14? No, it's not. Is 10 greater than 14? No, it's not. Is 10 less than 14? Yes, it is. So that means that this call returns a recursive call with the following parameters. Mid plus 1. So let's look at our current value of mid, which is 4. So 4 plus 1 is 5. And then everything else, so max does not change. We just use our current max, which is 9. And our target's going to remain constant throughout this whole example. Okay, great. So what we do next is we draw another arrow down here to indicate that we're calling recursively again. And we basically just repeat this process. Okay, so we do min equals 0. Sorry, no, we don't. We do min equals 5. We do max equals 9, it didn't change. And we do target equals 14, also doesn't change. Okay, so our max, if we look at our code now, our max is still at least equal to our min. So that means we've got to work out what mid is. So we calculate mid by doing min plus max, which is 14, integer division by 2, which is 7. Okay, so let's figure out what data 7 is. So let's see, that's 0, 1, 2, 3, 4, 5, 6, 7. So data 7 is equal to 18. Okay, so now we go through the if statement. Is 18 equal 14? Nope. Is 18 bigger than 14? Yes. So this one returns a recursive call to binary search with these arguments. Okay, so our min hasn't changed this time. We just used the same min that we're dealing with in this call, which is 5. But you can see that our max gets replaced by mid minus 1. So mid was 7, so 7 minus 1 is 6, and our target does not change. Okay, so it's time to recurse again. Okay, so let's see what the details are at the moment. Okay, so min is 5. We're just getting that from this argument list. Max is 6, and target is still 14. So our max is still at least equal to our min. Therefore, we got to work out our mid. So 5 plus 6 div 2 is 5. So what is located at data 5? 0, 1, 2, 3, 4, 5. That's 12. Okay, so is 12 equal to 14? Nope. Is 12 greater than 14? Nope. Is 12 less than 14? Yes. So we go over here. So we are returning another call to binary search with this specification. So mid plus 1 is 6, and then max, which is 6, and then target, which is still 14. Okay, we recurse one more time. Okay, so min is 6. Again, I'm getting this info from the arguments that were passed. Max is also 6, and target is 14. Okay, so max is equal to min, which means this up here is still true. So we need to work out our mid. Okay, so mid is 6 plus 6 div 2, which is just 6. And then we've got to find out what is located at data 6. So 0, 1, 2, 3, 4, 5, 6. That's 14. Data 6 equals 14. Okay, is 14 equal to 14? Yes. So we return mid, which currently has a value of 6. And that is the end of our recursive trace. Okay, so our final answer is going to be this right here, this 6. Okay, so I hope this made things a little bit easier to understand the recursive version. If you're still lost, I suggest following through this process yourself. Try some different values, try some values that are not in the array to figure out where the kind of -1 comes from. Just keep trying it out, basically. Okay. All right, so that's everything for this video. I hope you found this useful, and I'll see you in the next one.